All right. Hello, everybody. Welcome to class on Wednesday. We will start now. So if you're here, please turn on your cameras. All right. So we're going to continue from where we left last time. So to remind you, we're talking about statistics and stats, and we start talking about descriptive statistics and what are the some numbers, some figures we look at in order to summarize how a sample of data looks like, or how like a data set look like. And then we talked about so we talked about the mean, median, mode, and then we can start talking about end up talking about the range and standard deviation, and continue talking about standard deviation. So standard deviation is what is the point of standard deviation? So standard deviation basically is telling us like how spread the data set we have is, or how spread out the data set we have is, right? So we mentioned before that you can calculate the variance, that is to say, the average distance of a given point, or like the average point from the mean point or the mean score, right? So how farther away each point on average is from the mean, right? And the standard deviation is just the squared root for that, because as we said, in order to get rid of the pluses and minuses, you just want to see on average, well, how many points is it from the mean. We raise it to the power of 2, and then we take the square root, and so that standardize it basically. And so to give an example, like just to show like how standard deviation could be useful to understand the data. So if you look at this table right here, on this slide, so we have, so this is like, assuming like you have a number of people, and this is their heights in centimeters. So we're using metric system in this one. And so this is the actual heights, 170 centimeters, 0.18, 157, 72, 80, 65, 57, etc. And so here the mean is, is 168.4. Let's say 168.5. So that's the average. The range, which is basically we subtract the highest value, in this case 185.4, from the lowest value, which is 157.5, and so it's around 28. The variance is we described, so like, yeah, how far on average a point is from the mean, and then that's the standard deviation. Standard deviation here is around 9 centimeters, 9 centimeter 0.07. Say, let's say 9.1 for the sake of simplicity. So 9.1 centimeters is the standard deviation. What does that mean practically speaking? So when we say a standard deviation is 9.7, that means on average, that's the key point. Each unit in here, each individual is 9.1 centimeters higher, like taller or shorter than the median, the mean, right? So on average, each individual is 9.1 taller or shorter than the average height, right? So average height in this case is 168.5. which means on average, the other individuals are either 9.1 shorter to 9.1 taller. So that's basically where the average unit is. And when we say average, right, so that's the key point. We're not talking about a specific individual in this data set or in this table. We're taking it into totality. So that would mean some individuals would be, like in this case, for example, would be 2 centimeters away from the average. So let's see, like here, for example, almost 2 centimeters or 3 centimeters away from the average. Right here, it's like 2 centimeters, 180, 260. So it's almost like 1.5 centimeters. And so some would be further away, like 185. So that's like a 16.5 centimeters almost. The point is, on average, that's how far a score would be from the mean. Okay, so that's the first thing. Why do we care about this? So why does it matter? Because calculating the standard deviation would give us what we would call the the distribution of the score, or the normal distribution, or like that. So I would guess most of you have heard that phrase before: normal distribution, or distribution of scores, or the bell curve. Maybe you heard about the bell curve, or the curve or distribution, or a histogram. And so in the histogram, you see right here, so this is a normal distribution, and not all distributions are normal. Why do we call this a normal distribution? So there are 2 roles or 3 roles, depending on how you count it, to consider a distribution normal. So in a normal distribution, 68%, so almost 2/3, but this is more precise. So 68% of all the scores fall within a standard deviation from the mean. So in this slide, you see the mean right here. So this is the mean. This is the mean right here, right? And so 68% of the scores would fall in this range, right? Here, that's 68% of the standard deviation. Then it also says 95% of all the cases should fall within 2 standard deviations. And so when we say 68% and 95%, that plus or minus, by the way. So it would mean, as you could see right here, 34% plus and 34% minus. So 34% would be in 1 plus standard deviation, and 34% would be 1 minus standard deviation, right? So would fall within here. So in 95, the same thing, right? And so you will get 2 standard deviation plus, or 2 standard deviation minus the mean. So it would say in a normal distribution, the vast majority, almost, so 95% would fall within that range. And then we would say 99.7% of the data would fall within 3 standard deviations, plus or minus from the mean. And then the other, you would say what happens to the other 0.3%. So then there's no role for the other 0.3%, because those would be considered extreme. So they could be 4 standard deviation away, 5 standard deviation away, to infinity, depending on whatever case you're looking at. So to go back here, let's look at a concrete example to understand what this means. This means that the standard deviation here is 9, so it's almost 9.1. Let's say, call it 9.1. Okay. That means 68% of the cases, or of the individual in this population or in this sample, would be 1 standard deviation plus, so that's 9.1, plus the mean, which is 168.5. So that will get you to 177 0.5 or 0.6, 177.6. So that's 1 standard deviation above, and 1 standard deviation below, so 9.1 minus 168.5. So that would be 159.6, right? Give or take. Yeah. So 68% would fall within that range, right? Okay. And then if you would add 2 standard deviation, that means we're talking about like almost 18 centimeters. So again, 95% should fall within. So 18 plus 168 would give you like around 187. And then 2 standard deviations below, so 18 minus 168 would give you around 140 centimeters. So we would assume if this was, and only if, this was a normally distributed data set, that yeah, 95% of the cases would fall between 150 to 186, we said, or 87. Okay. Again, why should we care about this? So why do we care about how the data set is being distributed, right? What's the point? So remember we said descriptive statistics aim to summarize how the data look like so we can make an assessment, right? So right here are the people tall or short in our sample. So we want to know that, right? And so it's important to know not only the average, but also how distributed the units. So either we are measuring individuals or things or objects or channels, you name it, like how the units are distributed. Because when we have normally distributed data set or normally distributed group, we can then actually make generalization about it when we try to compare it to another group. All right. That's because we want to know how many extreme values exist in the data set that might alter the numbers that we've been talking about before, such as the average or the mode or something. But let's talk about an example so it would maybe become more clear why it's important. So suppose you have 2 classes, right, or 2 groups of students that just took an exam, right? So the exam is out of 10, right? So the maximum score is 10. And so here are the scores. So you could, if you could look, see right here. Here are the scores. Oops, sorry. Right here. So class A, so this is what the students got. So one got 5, 5, 5, 6, 6, 7, 9, 10, 10. Class B, 3, 4, 6, 7, 8, 8, 9, 10. Yes, by looking at it. So which class do you think did better in the exam? Class A or class B? Which class do you think did better in the exam? You can answer in the chat or verbally or any way you want. Okay.
We can't see the numbers anymore.
Can I see the numbers?
Yeah, they're back.
Oh, okay, sorry. So yeah, which class did better? What do you think? Just test of impression? Like 1. So we have, okay, so Olivia, Lily, Diana, okay. Nice, okay. Okay, so those of you Okay, so if you say class A did better, why did class A did better? Why do you think that's the case?
There are more scores in Class A that are higher than those of Class B, than vice versa.
Oh, okay. So you're saying because there are more students in Class A who got full scores, then Class A did better.
Not necessarily like just the tens. I mean, just like across the board, there are more scores that are higher in Class A.
What do you mean by higher?
Like if you compare each number, like I went through and there are like 3 in Class A that are higher than Class B, 3 in Class B that are higher than Class A, but in the end, there's more in Class A that are higher than Class B.
Okay. So if we do one like mano 1-to-1 matchup, so yeah, like here, so this is like equalized. So here A is better, A is better, A is better. Here B is better, B is better, B is better, B is better, A is better, A is better. So that's like some sort of a comparison. Okay. Who else? So yeah. So any other explanation why you think Class A did better?
I also think that when you're thinking about like an exam specifically, it's better to have like the range to be a smaller range. And in Class A, the range is smaller because it's like from 5 to 10 instead of from 3 to 10.
Okay, so you're saying, yeah, that's very interesting. So the range is from 5 to 10, right? Okay, so it's like 5 points. Whereas in Class B, it's from 3 to 10. So it's like, okay. Okay, so we have the range. What would be another way to compare Class A to Class B? Ideas based off what we studied at lecture? Let me ask. Gianna, are you here?
Yeah, I am.
Okay, so my question to you, how do we know if Class A is better than Class B? What are the things that we should look at? One thing we should look at.
I see that they have higher numbers in total, and so like a less of a distribution, so closer. What is it? More similar numbers.
What do you mean higher number in total? What do you mean?
There's not as many outliers as there are in Class B because I see there's a 3 and a 4, where Class A goes from 5 up with repeated numbers.
Okay, so you're saying lack of outliers. Is there one number that we can look at and tell us if Class A did better than Class B?
I guess 3 and 4 are the 2 outliers that I see. And then for Class A, there's repeated 10s.
Okay, so yes, okay, so that's a good one. So based on the outliers or extreme values, we want to see, yeah, which one had higher or like more positive outliers, and so that could determine. Okay, so that's also another way to look at it. What else can we calculate? So let's see here. So,
If you calculated the average, maybe?
Okay, yeah. Could you calculate the average then? Can anyone calculate the average if you haven't done already? Please calculate the average for class A and the average for class B. And then let's see how it is. Okay. So 7.3 here and 7.1. Okay, gotcha. Okay, now looking at the average scores, all right, it's 7.3 really different than 7.1. What do people think? Okay, so Larry, you say no. Why no? Why not?
I mean, it's only like you know, a 0.2 difference. Still would be C's.
Yeah, right. So so the two, it's a 0.2 difference, and that could be attributed to what? Why do we see a 0.2 difference?
I guess it could just be like one kid having a really bad test score.
Yeah, and who is that person in this data set?
Probably the 3.
Yeah, so here. So this person basically, yeah, just assuming this person received, so one person received 5. What would be the average score for class B? I'll do the calculation real quick. You'll add 0.2. It's 2 points, and you have 2. So add 0.2 to 7.1. What would be the average for class B? So this person got 5. Okay, this is 5. The average would be what? What would be the average? 7.1 plus 0.2. 91, just say it or type it. Yeah, okay. Yeah. So it's 7.3. So the point is, one person changed the average score for the whole class, which would give the impression that class B, on average, or in total, as Gianna was saying, did more poorly than class A. Where in fact, the thing is only one person pulled the average down for the whole class. And because we have a small sample, because they have 10 students in this class, yeah, like one person could have, like I said, a huge impact, right? Okay. And here it's the same. So if you look on here, if this person, for instance, like scored a point lower, so 9 instead of 10, that means the average score would have been the same in the two classes as well, right? And so this is the question, like, into why then should we only look at the average to determine which class did better, or do we need to look at other things as well, right? And so that's why we've been talking about distribution. And so if we assume each class is having the the scores distributed normally, okay, then when you have an average score, you want to know if those differences in average are not being caused by only extreme values. That the distribution of the scores within each group is the one that is different than the other, that caused the averages to vary. All right. So assuming there are no extreme values in each one, either on the positive side or the negative side, just looking at the average score is going to be tricky or misleading. Hence, again, we were talking about the mean and also the median and the mode and the standard deviation as well. Because the standard deviation could tell you how distributed each sample is, right? So if you look at this sample right here, if we, so right here, if we're looking at the median, okay, so the median would be here, okay? The median score for class B is actually higher than class A. So the midpoint student in class B actually did better than the midpoint student in class A. Okay, so that show like you could look at some numbers that show that class B is better than class A, or if you look at the average, so on average class A is to class B. But that's why we need to look at the distribution within as well to know what is causing that change or difference in the average score, right? And this would become an issue of importance when we're talking about inferential statistic or comparing groups later. Okay, so that's for those descriptive statistics. Now there's also another type of descriptive statistics that is getting us closer to inferential statistics. So here we are having so here we're doing a comparison. We'll do a cross tabulation. So a cross-tab or cross-tabulation analysis is when we compare the frequencies. And to remind you, the frequencies simply mean the counts. So how many cases appear for whatever subcategory or group you have. So the frequencies of one variable to another variable, right? i.e., it's a comparison of proportion. So what proportion of groups in this variable belong to which groups in the other variable? Okay, an example would be like a frequency of gender by ethnicity, or home ownership by geographic location, or like home ownership by gender. Like any two variables could be matched, right? So if you take a sample of students at University of San Diego, like we like the frequency by gender and let's say race. So like how many females, so it would be females who are white, males who are white, females who are non-white, males who are non-white, etc. And we see if there's like a different proportionality. So maybe it could be one gender has a higher proportion of one race or vice versa. So that's cross-tabulation, what our cross-tabulation meant for, to show you the distribution between two variables. So to look at an example here would clarify things even further. So assuming, so here this is data about smoking or smoking habits, if people smoke cigarettes or not. And so here's a count again, frequency. So do you smoke cigarettes? So we have three categories in here. So we have non-smokers, past smokers, and current smokers. And we have gender, right? So it's smoking status by gender. So non-smokers, you would see 149 male, 148 female. Past smokers, okay, so 50 male, 50 female is like 24. So we have more females who are past smokers than males. And current smokers, we have 31 males and 37 females. So we slightly have more current smokers who are female than male, only like by 6 individuals. Now we look at the total. So we have 193 males and 209 females. What would be the issue with the totals, though? What's the issue right here? What do you notice? But you know, it is in the total numbers. What's the issue?
There were more women in the study than men.
Right. So in this sample, there are more females than males. Why? How would that matter? Why should we care about that? What's the problem with that? So if we want to run a comparison between females and males, what's the issue of having more females in the sample than males?
It can throw off your data. So if there were more women, for example, in this one, even though there's about the same amount of men and women who are non-smokers, it doesn't matter because more women were counted for, therefore they'd have a lower ratio.
Right, right. So it's it's throwing up, as like to use the Gianna's phrase, it's throwing off your data. That is to say, it's throwing off your data. So it means that here it shows us that more females, even slightly, but more females are current smokers. But that could be attributed to just the fact that we have more females in the sample. All right. So that's something. So, and then if you just look at these two numbers right here, you would say there are more females who are smokers than males. And remember the thing about generalizability. So you would assume, even in the population, there are more females who are smokers than males. Okay, but that's just because here there are more females. How would we control for that then? What would be the number that we should compare to control for the difference in the total? Can anyone guess? You want to look at the proportion? What is the word similar to proportion?
Ratio?
Yeah, ratio or proportion, ratio, and then we could calculate also what?
Percentages?
Yeah, percentage. Yeah, ratio percentage. Yeah, right. So could someone real quick calculate the ratio or percentage for females who are current smokers? So 37 out of 209, and males who are current smokers. So 31 out of 193. What are the percentages? Please tell me you know how to calculate a ratio. It's just division. Okay, so it's 17 for females and okay. So 17.7 of females, 16.06 of males, correct, right? So yeah, so in this case, then it's right. So there's a higher percentage of females who are current smokers than males who are current smokers. So 17.7, assuming Eric's numbers are correct, but I'm just kidding. And 16.06% of males who are smokers. So that's a more accurate way of doing it, right? Because now we're looking at comparing proportionality to proportionality, right? And if that's the case, so that we did this for current smokers. Now look here, the one I already circled. Can you calculate the ratio or percentages of females who are non-smokers to males who are non-smoker? What are the percentages? Okay, so 70.8 for females and Okay, and 77.2 for males, right? Okay. So here we're having like, yeah, so it's a point, it's actually, yes, it's a minus or plus here like a 7 percentage, right? 7 percentage difference between males and females. Here it looks like it's the same, but when you did percentages, it's actually a significant difference. So we have 77.2% of males who are non-smoker versus 70.8% of females who are non-smokers. So the numbers look the same. If you just look at it, you see, okay, it's the same proportion of males and females when it comes to non-smoking. It's actually in this sample, and it's just a made-up table, by the way. Males, yeah, like tend to have more non-smokers than females, right? So that's the that's what cross tabulation does. It shows you percentages, and we're going to show you another example in a second. So assuming, for instance, that this is just the frequency table, just the number of counts. So this is a question: what's your primary or the most popular medium for news consumption, or you use for news consumption? And so we have printed newspapers, online newspapers, TV news, radio. So we have here number of responses and percentages, right? So this is from the whole sample. And so you could see here that the majority, like plurality, do like printed newspapers, okay? But then we can do a comparison. And if you look at the comparison, you would see, for instance, that we were doing comparisons by age groups. So you would see that when you do per age group, you would see that printed newspapers are more popular with people who are older than 45 years old. Online newspapers, it's more popular with people who are 18 to 24. TV news is more popular with people who are like 25 to 34, people who are around my age. Radio is also popular with people who are older than 45 years old. So here, this is another function or use of frequency table. Is that, again, so here we're comparing one variable, which is use of medium for news or for news consumption, and age. That's the other variable. And we want to see if that first variable, news consumption, vary according to the other variable, which is age group. Okay. And so he is showing you the differences in numbers. And then you can then calculate, because you have the total, what percentage of people who are 45 years old watch or listen to the radio versus other percentages from the other age groups, which will give you even a more accurate assessment. So that's one way of, so this is still considered descriptive statistics, but you could see it could tell you something about the sample. It could tell you some relationship that exists between variables within your data set, right? So in this case, news consumption by age, or smoking by smoking status by gender. So that then moves us to talk about descriptive statistics, which we're going to talk about it on Friday, and which go beyond describing how the data set look like into trying to test the relationship between variables. And that has been the objective of quantitative research. As we've been saying, quantitative research aims to be explanatory and predictive. So it can explain why two variables have a relationship. To remind you, the relationship be a correlation or a causation or lack of a relationship, right? You could predict a change on Y based on change in X. So the outcome or the dependent variable changes based on changes in the predictor or the independent variable. And it can also allow you to measure differences between two groups. So statistically, we want to see. So instead of just judging by, okay, how many individuals scored the highest score or just eyeballing to see how many extreme values are in the sample. We want to see statistically, we want to have an established, reliable test to see if a difference in average is significant or not between two groups. And that's something we're going to learn in the coming 2 weeks, right? Like, how do you know that the difference between two groups is significant or not, statistically speaking? Unfortunately for you, there's not one test that fits all. The tests vary, or like we have different tests for different data types. And so the things we are going to cover in this class are the following. So these are the inferential statistic tests we're going to cover in this class. First one is called chi-square, which is used for testing difference in a cross tabulation. If you see in the cross tab and we want to see if the two proportions of the two groups are actually different, we will conduct a chi-square, and we're going to practice this actually. And then we have two t-test, which is to compare two groups, so the average scores for class A to the average scores in class B, or one group at 2 points in time, which is basically the same mathematical test. So how group A did in exam 1 versus exam 2. If we have two groups, we use t-test. If we have more than two groups, we use ANOVA, which stands for analysis of variance. That's an acronym. So if you're comparing 3 groups or more, you'd use ANOVA. It's basically the same test, give or take. Like, you want to see if the average score of group A is different than group B, is different than group C. And you can go more than 3 groups. And we're going to study correlations. And that's basically, if two variables change together, right? Or covary together. To remind you, those picking which one is appropriate depends on the level of measurements we're going to use. So can someone remind you, like, what type of or level of measurements we covered? So we said the variable could be measured. Are they going to have nominal variable? And then we had 2 other things. So we said we have nominal and what? Anyone remember? So we have nominal variables, and then there were 2 other types.
Is numerical one?
Before numerical, which one would we say? So we have nominal, and then
Is the next one categorical?
categorical covers. So yeah, categorical can be nominal, or what's the other thing? Yes, ordinal. Thank you, Anais. Ordinal. They have nominal, ordinal, and then we have continuous, and also continuous is also called numerical. So the difference is ordinal. So nominal is by name only. So the numbers have no actual value. Ordinal give you a rank or an order, but the numbers aren't real. So they don't have intervals. So they just give you a rank. So first place, second place, third place, but doesn't have like this. So there's no 1.1 or 1.5. Those are distinct ranks. And continuous, because it's an actual number, so you can do an interval comparison. So from 4.3 is higher than by 3 points than 4.0. So the numbers there are real, and just there's a technical difference. If it has a real 0, it would be called a ratio. It would be an absence of something, right? So like an absence of height or an absence of weight. Or like absence of money. So the negative is an actual negative, and the zeros are actual zeros, and not just conventional measurements that we constructed, right? And so the advantage numerical gets you is that it would be more precise in how you measure. right? So if I compare your test scores, better than if we say who got A versus who got B versus who got C, right? Because I could be more precise. Yeah. So A, B, C, that's that on ordinal scale. Actual scores, so 198 out of 200, for example, that's a continuous or numerical. So that's it for today. I'm going to post an exercise online, and so you use Excel. Make sure all of you have Excel installed. I already reminded you, and so before you do that one. So we'll do more of exercises, yeah, also next week. Do you have any